Hi, everyone. Welcome to this week's Crunch seminar. Today, Kyriakos Georgiou will be presenting his work on explainable machine learning with Fredholm neural networks. Kyriakos is a postdoctoral research fellow at the University of Naples Federico II under the Future of Artificial Intelligence Research Program, focusing on the intersection of numerical analysis and machine learning. He completed his PhD at Athens University of Economics and Business, where his research focused primarily on jump diffusion processes, PDEs, and machine learning. He completed his bachelor's in pure mathematics at Imperial College London and his master's at LSE. Kyriakos is also a co-founder of the Greek startup Finloop, which has received over 1.5 million euros in funding, where he previously developed machine learning models for instantaneous credit risk scoring. For this work, Kyriakos was included in the Forbes 30 under 30 list in Greece. With this introduction, I invite you to present your work, Kyriakos.
Thank you very much, Vivek, for this introduction. And I'd like to also thank very much Professor Kaniadakis for the opportunity to present at this seminar. It's a great honor. So as Vivek said, I will be presenting our work entitled Explainable Machine Learning with Fredholm Neural Networks. This work was done with Professor Sietos and Professor Giannakopoulos, who is the advisor of my PhD. So just to start off with a bit about what I will present to you here today. In this line of work, our goal overall is to draw comparisons between neural network architectures and classical numerical schemes. So our goal is to construct neural networks specifically that can approximate solutions for integral equations and PDEs, but also adhere to some underlying mathematical properties that classical numerical schemes can be proven that they satisfy. So the structure of this presentation will be as follows. I'm going to talk a bit about the motivation behind this approach. I'm going to show how we were trying to connect fixed point estimations and neural networks in order to solve, firstly, Fredholm integral equations. We're then going to talk about the extension of this method that can be applied to elliptic PDEs, and this is done via the potential theory approach and the boundary integral method. I'm going to show some results that we have for these neural network constructions that pertain to error analysis and explainability, which again, we can look at through the lens of numerical analysis and numerical methods. And I'm also going to present some applications to inverse problems that we can use this framework for. And specifically, what we're going to see is that using this framework, we can learn functions, we can train models that can adhere to some necessary mathematical properties that we need in order to define our equations rigorously. And also, I'm going to give a bit more details about some future work directions that we are considering and are very happy to discuss. So, a bit about the motivation. I think everyone in the field is well acquainted with the issues pertaining to the lack of explainability and the lack of interpretability, specifically regarding deep neural networks. So this is considered somewhat of an open problem in scientific machine learning. So obviously this creates issues that are important in terms of application. So if we're looking at these big models applied to cases like medical imaging, etc., or even credit risk models where these models adhere to some regulations and some explainability constraints, this is a very important problem and has to be considered. So from a theoretical standpoint, what this means is that we're interested in connecting the models, some neural network, its internal calculations with the resulting errors. So if we have some errors from our approximation, we want to find some way to connect this with the internal calculations that are being done within the model. So our main focus is going to be to address these problems using what we are calling some kind of numerical analysis-based construction of neural networks. And this is going to allow us to solve forward and inverse problems for integral equations and extend also to PDEs. I should mention, which is important, is that this, of course, is not a new approach. There are many seminal papers regarding such connections. I have some bibliography at the end that I would recommend for anyone interested in these problems because they're very, very interesting work. Specifically, what our approach details in the presentation is on these two papers. So the first is entitled Fredholm Neural Networks, where we first present this framework, which is just been published in the SIAM Journal of Scientific Computing. And the second one is currently in a preprint where we detail all the mathematical results regarding the application of Fredholm neural networks to forward and inverse problems, specifically now for elliptic PDEs. So to start off with the construction of this method, we're looking at Fredholm integral equations. This is the mathematical motivation behind this construction. So if we consider Fredholm integral equations of the second kind, which are equations as given here, so we have a linear integral equation and the corresponding nonlinear case. What we know from Banach's fixed point theorem is that these can be solved using a fixed point scheme. So we can reach the fixed point approximation that solves these Fredholm integral equations using the method of successive approximations. Specifically, this requires the integral operator to be either a contraction, so a strict contraction, or non-expansive. And specifically for the non-expansive case, we can apply the Krasnoselski-Mann method. So this is the most general method that we can apply in the case that we have a non-expansive mapping. And the calculation, each iteration is given by this calculation in equation 2 here, where each step is just this linear mapping of the previous step and also depends on the integral operator applied to our previous step. So obviously in the case where t is in fact a contraction, this simplifies and we just get that f of n is the integral operator applied to f of n minus 1. And by Banach's fixed point theorem, this converges to the fixed point solution. So the idea is that we can discretize this by a simple naive discretization of the integral operator, and we can write this as this sum. So if we define this operator to be the operator that corresponds to the discretized version of the integral for some fixed over some fixed grid, then what we can write is that this operator is just these constants from the Krasnoselski-Mann algorithm, kappa n times g of x, and we're also discretizing the integral as we see here. So this is just the Krasnoselski-Mann algorithm, but in a discretized version. And we can apply this m times, so this is just a composition of these operators in order to get what we called a m-layer deep fixed point estimate. And the reason that we kind of confuse this terminology with the deepness of neural networks is because we can look at this as just the calculations done in the in a simple feed forward, fully connected neural network. So as an example, if we consider a contractive operator, so in this case, we can just apply the successive approximations as given by equation 3 here. We can discretize, and this is our first. In the red, you see the first iteration. So let's say f of 0 is just our g of x, which is known. We multiply by the kernel k. We add g, and this is like multiplying by the weight and adding the bias at each node. And then the result of this layer, so the output of the layer, is then again multiplied by a weight, and we add the bias. So this is exactly just simulating the feed-forward calculations that are done inside a neural network. This is just this simple idea of connecting this discretized sum with these linear calculations. And this gives rise to this construction of what we called a Fredholm neural network. So we're saying that the m-layer approximation to the fixed point solution for our Fredholm integral equation can be implemented as a deep neural network. with m layers, a linear activation function between each layer, and weight matrices and biases that are given by these deterministic closed form representations here. So in this construction, what we have is that the diagonals are what correspond to the Krasnodębski man correction terms. I'm just going to go back and forth to show this. So this term here, that is the correction term that is needed when Zj is equal to x. This is captured in the diagonal of the weight matrix corresponding to us going between each layer. And again, the biases are also deterministic and just depend on and are given in exactly how the Krasnodębski man algorithm is implemented as well. And of course, in the case where this is a strict contraction, this simplifies further, and the diagonals are just the kernels, as are all the other entries as well. So this gives rise to this very custom universal approximation theorem, if you will. So what we're saying here is that in the case where we're looking at functions that are solutions to some Fredholm integral equation, these can be solved by a deep neural network with a custom activation function, where our first activation is just given by basically our first guess of the solution. So a simple case would be just to start off each guess with this known function g, and then the rest are just linear activation functions with known weights and known biases. And this allows us to get an approximation which is as close to the true solution as possible. We know this because we're just simulating the method of this successive approximations in order to reach the fixed point. Now, of course, again, I'm stressing this because we're going to see how it helps us when we're not in the case of deterministic weights. But right now, we're looking at approach which is purely constructive. So this means that we have a deep neural network that is connected to a numerical approximation scheme through which we can now calculate a priori error bounds. And we can also, on the flip side, determine the required depth of a deep neural network without any heuristic tests that are needed after training. Because now the proposition here says that the M-layer Fredholm neural network, the error in this model is bounded by this expression here, which is easily provable using the triangle inequality and decomposing this error into the error component arising from estimating the fixed point solution and the error arising from the integral discretization. And solving this for M, we get the necessary depth that is required for a Fredholm neural network in order to be epsilon close to the true solution. A very simple example is this Fredholm integral equation you see here, which the kernel depends on is sine of x times cosine of y. We create a grid. So this grid corresponds to the nodes in our Fredholm neural network. And we apply the method of successive approximations m times, where m corresponds to the depth of the neural network. And in the graphs, you can see the corresponding solution, so the fixed point estimation. And we also see that, as expected, the errors do indeed decrease as we increase the number of layers because we're approaching the fixed point solution. So now to get into how we can use this to solve forward problems and PDEs, which is a bit more interesting. So we consider the two-dimensional.
Kyriakos, before you go to the PDs, I
Yes.
have a question on the previous one. How accurate is it? Because we cannot see from that scale. Do you get down to machine accuracy, for example, by increasing the number of layers, or you saturate?
So yeah, it depends actually on the discretization scheme. So for a simple naive discretization scheme of the integral, we get down to something like 10 to the minus 7 in the example that we saw here specifically. However, when we applied this to the PDEs, which we did in MATLAB, we got down to almost machine precision. So the errors were about 10 to the minus 13.
Right. I'm trying to check if that affects the um, roughness of the lost landscapes, which probably you're producing smoother lost landscapes. That's why you overcome the optimization error.
Right, but here we are not. We're not actually
Doing
learning it.
optimization.
Yeah, right. So yes, this is the pure deterministic approach
Right.
so
Yeah.
far. Yeah.
Yeah. So that's why you get the machine accuracy. Yeah.
Exactly. Yes, of course.
Thank you. You can proceed.
Thank you. So right, going down to the PDEs, we'll see again how we can use this construction in a way that can be applied to elliptic PDEs, because and the reason is because the solution to elliptic PDEs is connected to potential theory, what we call potential theory, and the corresponding boundary integral method. So to build up this approach, we're going to consider just a simple two-dimensional Laplace equation for with a simple boundary condition, a Dirichlet boundary condition. And from potential theory, what we know is that the solution to the PD can be written via the double layer boundary integral, which is given by this integral, which we call P of x here. So this term depends on the normal derivative with respect to the fundamental solution of the Laplace operator, as well as this auxiliary function vita. And vita is the solution of the boundary integral equation, which is given by equation 13 here. And as you can see, it's a Fredholm integral equation. So our idea here is we can find a way to write the solution of this PDE using Fredholm integral equations and trying to include in this deep neural network construction the form of this double layer boundary integral. To do that, however, we have an issue which is related to the jump condition that occurs on the boundary when we use double layer potential integrals. So specifically, what we have is that this derivative here is actually proportional to the inverse of the modulus x minus y. So as x approaches the boundary here and the value of y, this blows up numerically. And it can be shown, this is exactly a jump condition, that as we approach this limit, the double layer potential has to be corrected with this 1 over 2 vita term. So this is the well-known jump condition that holds for double layer potentials. So in order to get strictly our boundary condition as we're approaching the boundary, what we have to do is account for this additional term. And when we do that, we get that u of x, or our double layer potential plus this term, is identically f. And so we have two problems here. The first is, how do we calculate this numerically, given that it starts to blow up as we're approaching the boundary? And the second is, how do we account for this jump condition smoothly as we're approaching again the boundary, so that we don't have to add by hand somehow this additional term. And our idea here was to go back to the proof of the jump condition. So when you're proving this limit, so when we're proving that as x tends to y, we're getting this additional term here, we can actually take a previous form of the integral representation, which is more smooth numerically. And this is exactly the form that we have here. So in this form, we see that as y tends to x star, which x star is some point on the boundary, is the point corresponding to x, but on the boundary, this term is going to blow up. However, we're also going to be approaching the first term here, vita y minus vita x star, is also going to be approaching 0. So our hypothesis was that if these two somehow cancel out, that this can provide a more smooth approaching of the limit. So what we showed is that this indeed does happen. So in this way, we were able to actually approach arbitrarily close when we implemented this in the code as well. We were able to approach the boundary arbitrarily and still get accurate solutions. So, and the second advantage of this is that it's an integral, so that means that we can again write it as an additional layer in a deep neural network. It's a discretized linear mapping. So again, it fits in our Fredholm neural network framework. So this is our construction. This is the explanation of our construction. And this entire now deep neural network with a custom architecture is what we called the potential Fredholm neural network. And its construction is exactly what we said. It's a first component that solves the boundary integral equation that gives us the function vita. And we solve that with a deep Fredholm neural network. And then the final layer reconstructs this custom integral representation of the double layer integral. So in this way, we have a custom architecture, custom connection with the last layer, but the solution in total basically just recreates the boundary integral method for the solution of our PDE. So as an example, we applied this to a simple Laplace equation with this boundary condition. And this is the exact form of the double layer potential as well as the boundary integral method. So we see that this here, we're in the case where this is a non-expansive integral operator here. So we do indeed need the Krasnodębski-Mann Fredholm integral, the Krasnodębski-Mann fixed point approach in order for this to converge to the fixed point. And that's what we implement in the Fredholm neural network. So applying this, we get this solution here and the corresponding errors, absolute errors, which are of the order of 10 to the minus 13 across the domain. Of the maximum is of the order 10 to the minus 13. And actually on the boundary, so you can't see it very well here, but these slightly lighter parts, which indicate a slightly lighter error, are near the boundary, but not on the boundary. So in most of this domain, we have an error of 10 to the minus 15, and on the boundary, it's around there as well. So this part is just right before the boundary. Overall, our idea was that perhaps this jump condition gives some insight into how and why perhaps sometimes increased errors can be seen in the boundary when we apply vanilla type machine learning or physics-informed machine learning approaches to PDs. Obviously, this is something which can be easily overcome, but just in terms of how a model learns, our idea was if we could write this in a slightly different approach, maybe there's a smoother way that we can write this in terms of a neural network model. Great. So in the follow-up paper, we wanted to generalize this. So we generalized this to Poisson PDs as well as the Helmholtz PDE. So again, we can write these in terms of this new, smoother representation of the double layer potential. So the math here is actually quite interesting. We have to get into the analysis of the double layer potential integral, and we proved that we can have these representations here. So for the Poisson PD, the only addition that is needed is this integral that corresponds to the source term. And for the Helmholtz PD, where we have a different fundamental solution, which is the Basel function, the modified Basel function here, we actually have a slightly different proof, which requires this additional term here, where we have lambda times delta f, where delta is this difference in the fundamental solutions. So overall, these two double layer potential representations, they give us, as we said before, in the potential Fredholm neural network construction, they again can be written as the final layer in this deep neural network, which means that we have to calculate these integrals, which are however, easily tensorable and discretizable. So this is not too computationally heavy. Finally, what we did is we also wanted to consider semilinear elliptic PDEs. So this is again in the second paper. And to do this, we considered a contractive mapping approach. So we want to again consider a fixed point approach that might be that would allow us to easily implement the potential Fredholm neural network construction. So to do this, we can take some lambda, which is sufficiently large to ensure we have a contractive mapping. We take some initial guess for the solution of our PDE, and then we can solve this Helmholtz PDE iteratively, right? Because at each step, we're just solving the Helmholtz PDE, knowing what UN is from the previous step. So this is something that we call the recurrent potential Fredholm neural network, whereby we're solving the neural network, the Helmholtz PD at each time. We're with, again, the first component being the Fredholm neural network that solves our boundary integral equation. And the last layer corresponds to these representations of our double layer potential. So in each step, given that our source term here depends on U, we have to update this this integral here, and we're feeding it back into this neural network. So these are there are three examples that we considered. Here are the corresponding error metrics. So we have the maximum absolute errors and the mean average errors, both in the interior and in the and on the boundaries of the domains. And as you can see, we have, especially on the boundaries, we are able to approach very, very good error metrics, so around 10 to the minus 15. And as well in the boundaries inside the domain, excuse me, we're looking at errors that are around 10 to the minus 10 to 10 to the minus 8. In order to go into now a bit the correlation, how we can use these architectures for explainability and error analysis, I'd like to draw your attention to this inset graph for the final PD here. So as you can see, we saw this very small increase in the error between layers 20 and 30. So when we actually increased the layers in our Fredholm neural network, in the potential Fredholm neural network from 20 to 30, what we saw is that we had a slight increase in the error. So given our construction, this seemed a bit counterintuitive. So this is where we posit that this representation can be helpful as a basis by which we can consider error analysis and explainability in these large neural networks. So given that we are constructing them a priori to simulate these calculations, what we have are a priori error bounds as well. So a theorem that we have is that given the form of the potential Fredholm neural network, specifically for the Helmholtz PD, but this also applies to the other cases as well, we can define these quantities here that all depend on the discretization error of our integrals. So here, integral tilde just, of course, it just represents our discretized integrals. And if these are the errors, so the norms of the errors of our integral discretizations, then our error in the approximation of the solution of our PDE is given by this closed form representation here. So we see a few interesting things. First of all, naturally, this depends on how well we are able to approximate the boundary function. So this vita. All these terms in the first parentheses are multiplied by the error in our fixed point approximation of this boundary integral function vita. However, we're also adding terms that depend on the norm of vita itself. So these are the terms here that you can see. This multiplies this discretization term D1, and also the term D4, which is this discretization error when discretizing the integral with respect to vita in the fundamental solution, also depends on the norm of vita. And this can easily be shown by that it can easily be shown that this D4 term is proportional to the error into the norm of vita m itself. So this means that we have this result that as the norm of vita increases, that we may observe increased errors as well. And this is, of course, I should mention that this is for a specific type of error, right? We're looking at, we've defined these norms to be that we're looking at the maximum absolute errors. But it shows how we can use these calculations in order to get some understanding of what is happening in terms of the numerical analysis behind this. And this can easily be extended, of course, to what we call the recurrent Fredholm neural network, the potential Fredholm neural network construction, where in each step, we're just solving this Helmholtz PDE. So this is exactly how we can explain the error that we saw between the difference that we saw between our approximation when we used 20 and 30 layers. We inspected this and we saw that when we applied 20 layers in our Fredholm neural network, the norm of vita was actually less than when we applied 30. And this multiplication then in our error result, we believe was what caused this increase in the this small increase in the error. And indeed, our approximation when compared to the true solution, when we used 20 layers was less than when we used 30, because this norm of the vita when we used 30 was larger. And then after, we see what we would expect was for m greater than 50, for example, where we've reached some plateau. So we've reached the vita m and the error in the fixed point estimate of vita have stabilized, and the error is constant no matter how much we increase the layers after that. So now I'd like to show how we can use this in perhaps more interesting problems that also have to do with inverse problems. So this is interesting because I believe it shows how we can connect these constructive approaches with classical training methods. So what we're going to try to do as a first case is we're going to solve the inverse kernel problem for a Fredholm integral equation. So we consider, for example, the inverse problem of finding the unknown kernel K, such that this integral equation admits this specific solution. So we consider that we have some known data points of our solution F at some predefined grid X of I. And so the inverse problem consists of the following. We are given the data. We also know the function G, and we want to model the unknown kernel so that it provides a consistent approximation of this integral operator. So this means that when we solve the Fredholm integral equation, our solution F should coincide as close as possible with the data that we are given from this for this problem. So our approach will be to pass through a Fredholm neural network. So given that we know that the Fredholm neural network is constructed so that its weights and biases depend on these deterministic parts of the integral operator. So, and specifically, we know that the kernel itself determines the internal weights of the Fredholm neural network. Our idea is to consider some model for kappa, for the unknown for k, sorry, for the unknown kernel. We feed it into a Fredholm neural network, and we look at the output of the Fredholm neural network, comparing it to our data. And then the training process is basically going through this loop and training and updating our model for kappa as we go along. So this is exactly what is described in this algorithm. So we are creating a grid given our known data points that are going to be used for training. We set the model for the unknown kernel. And for the number of training iterations, we construct a neural network, which we call FNN of depth M, with this kernel model as its input. We look at the output of the Fredholm neural network, which approximates the solution to our integral equation, and we compare the solution to the given training data that we have. Of course, because this is a integral equation, this is an ill-posed problem, so we need some kind of regularization term as well. So we consider two approaches in the example that in our paper. The first was a bit of a parsimonious idea whereby we just minimize the norms of the squared norms of the weights, and the second was minimizing the residual of the integral equation itself, with the idea being that on the one hand, we're passing through the Fredholm neural network, ensuring that that our learned kernel is obeying some contractive properties in order to reach a solution that is close to our data. And the second part, this regularization term ensures that at the end of the day, we are satisfying our integral equation. So this is the schematic given here. And the results that we had for a specific example where we considered 300 sample points, these were generated from a Fredholm neural network. And then what we did is we fixed a new Fredholm neural network. We considered 15 layers deep to ensure that we would have satisfactory convergence to the fixed point. Of course, we could have tried something bigger as well. And we also had 300 nodes per layer, which correspond to the grid on which we are calculating the output in order to compare it with our training data. We applied this approach. This method, and for this approach, we just considered the model for K to be a shallow neural network with a single hidden layer. And this training approach was done using a Levenberg-Marquardt algorithm in MATLAB. The results are given here, both using both of the regularization approaches. And as you can see, we had, I think, pretty good mean squared error values. And the corresponding L infinity, the maximum errors were about of the order of 10 to the minus 4 when we used the integral equation as the residual. Now, I'd like to discuss a bit the graphs as well that you can see here. The first is the bands, the uncertainty quantification bands of the output of our final trained kernel passing through the Fredholm neural network. So we have our outputted solution F, and we are plotting this along with our estimated data as well as the uncertainty quantification bands. The second graph corresponds to what we did is we took over all 50 runs that we did. We found the X value at which we had the maximum error over all 50 runs, and we looked at the distribution of the errors for this specific X value over all our runs. And our goal here was to show that the errors overall here are well distributed. And indeed, most of the times at this point, we had an error of less than 10 to the minus 3. So the specific larger error, which was around 10 to the minus 2, was only because of the standard randomness that one might expect when training such models. Of course, what I think is most important, what most interesting here is the fact that after we learned our kernel, we pass it through the Fredholm neural network, as we said. And what we did is we looked at the norms of the differences of the consecutive layers. And as you can see here, this is decreasing, which means that indeed it's a contraction. So we were able to learn K such that it's a contractive mapping. And this is, I think, quite interesting because we did a few experiments, of course, with just simple learning schemes, etc., where it's hard to guarantee that your output model will be contractive. So we are by passing this through the Fredholm neural network and populating our weights with something that depends on our unknown kernel, the calculations done inside the neural network make sure that the final model that you choose is indeed contractive. So it does adhere to the mathematical properties that you want. So we also applied this to the inverse source problem for the Poisson PD. So we have this Poisson PD. We consider some unknown source term psi, and the approach is almost identical, but instead now we're passing this through a potential Fredholm neural network. So now what we're doing is we're considering some grid, and we're going to consider some coarse training data, U, on this grid. We construct a large enough potential Fredholm neural network, and we model the unknown psi with some simple model. And we pass this into the potential Fredholm neural network, and we train by comparing the output with our training data U until we reach an output that is close enough to our data. We applied this to a given Poisson equation with this boundary condition here, and we considered training data over a grid of size 20 by 20. And we considered, again, a simple shallow neural network as the unknown source term psi. So we wanted to, we knew the true solution here, which is given by this expression. And we applied this algorithm. The results, again, were quite satisfactory overall, with an average final error after training and when comparing to our training data in the interior of around 10 to the minus 4. And what is interesting is that, as you can see, by this construction of the double layer potential, which holds by definition, by construction, I should say, sorry, our errors on the boundary are very, very small. So we have errors of the order 10 to the minus 15. So this goes back to this smooth double layer potential representation that we saw. Because we're passing our models through this Fredholm neural network, which is constructed this way, at the end, we get no matter what our model learned for the source term, we know that it's going to satisfy these boundary conditions quite well. In the graphs we
I have
see,
a question here. Excuse me.
yes.
So I can see that the error on the boundaries are very low. How about the error of like the derivative of the solution on the boundary?
So this is something that we didn't consider so far.
Oh, okay. Thank you.
But yeah, thank you. That's a very interesting comment. Thank you.
Okay.
So in the graphs here, we can see the learned solutions. We also see the absolute errors when comparing the output of the potential Fredholm neural network to our training data. And we also tested on some unknown test grid of size. We tried a test grid of 50 by 50. And we compared the output with our learned source term with the true solution. And what's good here is that we saw that our errors were of the same order, so 10 to the minus 3 overall, and the same was true for this unknown test grid with, again, very good approximations on the boundary of the same order, 10 to the minus 15. So to sum up, and apologies if I took a bit more, but the overall approach, so with Fredholm neural networks, we're trying to construct a framework where the result is a complete neural network where the hyperparameters are known. They have a direct interpretation that corresponds to classical numerical methods. This retains, by its construction, a high accuracy throughout the domain when applied to PDs, and particularly on the boundary through this representation that we saw, whereby this connection, we can also consider a priori convergence and error bound. And the final note is that with this approach, the model architecture itself helps us to be able to solve both forward and inverse problems whilst ensuring that our results are explainable, because we know how in the end they relate to the output of our problem, and they also admit some necessary mathematical properties. So, for example, as we saw, that we can learn a kernel which is in fact contractive. So, although this is a constructive framework to begin with, our idea is that this can be interesting as an approach, because it can be a somewhat different way of looking at populating these internal weights and biases, by which we consider some smaller model and then we feed it into a larger model in this larger model, the weights and biases are known, how they mathematically relate to this quantity. So, closing, I'd just like to say that we believe that there are new directions and some exciting research opportunities here that can be pursued. Of course, extensions to other PDEs by connecting these PDEs to integral equation representations. Definitely something that we are interested in is extending to nonlinear cases and more complex domain problems, because this is still what we've considered so far are very simple domains and PDEs. So we're looking at how we can connect this approach to more classical type of machine learning advantages that relate to perhaps using architectures of Fredholm neural networks, but also training methods from classical approaches, from scientific machine learning approaches. And finally, we are considering that this could have some applications in, of course, explainability, but also in uncertainty quantification, by using these as perhaps baseline models and custom models that we know have some error, some required properties, and can be compared to trainable models as well. So to close out, I'd just like to say that this, as I said, is in the direction of numerical analysis informed machine learning approaches that has very interesting literature. These are a few which we looked at, and in particular, this connection with integral equations and deep and feed-forward neural networks has been considered in other work as well. So, for example, this integral neural networks considered this connection, but in a slightly different way. And there are also other very interesting works that have to do with how we can use neural networks to simulate approaches that recurrent iterative approaches, excuse me, and how these relate to the explainability part of neural networks. So thank you very much. Thank you again.
Thank you, Kyriakos. It was a great talk. It was quite easy to follow. Now, I'll open the floor for questions. If anyone has any questions, please unmute and go ahead.
Hi, Kyriakos. I'm Kyle. I'm a student at Brown. Really interesting work. I have one question I didn't quite understand when you were introducing the inverse problem.
Okay.
So yeah, I think it's a slide 23. So when you're doing this, do you initialize a separate neural network to train for the kernel and keep the FNN fixed?
Yes, exactly. So what we are doing is we're saying let K be the output of just some small neural network, a simple, very simple neural network, and we're going to feed this into the Fredholm neural network, and we're going to look at the output. So yes, it's a separate little model.
Makes sense. So the K would go into so the weight of the FNN would depend on the kernel, the value of the kernel K.
Exactly. Yes.
Then is it doable if I do not initialize a separate neural network for K, but I make some of the weights inside the Fredholm neural network to be trainable, like all the weights that are related to K to be trainable inside FNN, and then I train this FNN instead of train the separate neural network for kernel. Would
Yeah.
that also be a viable approach?
That yeah, that sounds very, very interesting. I think that it's pretty much the same. Yeah, because you basically you're saying that you predefine the connection between these weights, right? So you have this relationship between the weights, and then you just train the Fredholm neural network instead of populating the weights with a trainable model, right?
Exactly.
Yeah.
Exactly.
Yeah, that I would imagine that that's a very, very doable, and it sounds very interesting. Yeah, and it's in this intersection between the constructive architecture and the trainable components that we want to consider as well.
Yeah. Makes sense. Yeah, thank
Yeah.
you.
Thank you.
Thank you, Kyle. I actually have a few questions.
Yeah.
So firstly about the scalability. So if I understood correctly, the different neurons in your Fredholm neural networks corresponds to the different elements or different mesh points, right?
Yes. Yeah.
So suppose you want to solve the Poisson's equation in a 3D state, like with X, Y, and Z components.
Hmm.
So obviously, at some point you'll run into out of memory. So could you do
Right.
something like a badged version of this thing so that you could manage without running it out of memory? Can you batch the Fredholm neural networks? That's my question.
Yeah, Vivek, this is I completely agree. This is something that again we are very interested in is because so this is kind of a constructive framework, the basics of the framework that we're trying to consider here. The case of high dimensional problems is something where again you're kind of running into this. I mean, maybe I'll lose it. I'll use it a bit loosely, but this curse of dimensionality, right? You get this again, this issue with the grids and everything. So yeah, I think there is where again you can use the helpful, very important approaches from machine learning, like batches, like maybe even separable training approaches and stuff where you
Right.
can consider, these like separate little Fredholm neural networks or whatever, and
Understood.
train these counterpart and these specific parts. Yeah.
Thank you. I have another question. So if the forcing function, that is clear. Thank you for explaining. It was pretty clear.
Thank you.
So I have a different question, which is, suppose your forcing function has high frequencies. Like instead of saying pi x, let's say you have like sine 50 pi x or 100 pi x.
Hmm.
Did you try an experiment like that? Did you struggle, or what do you expect to get?
We didn't try something like specifically to kind of test the limits. So
Right.
we haven't really tried something like into to the extreme of such high frequencies might be.
Uh-huh.
But so my intuition based on what we've done so far, if we're talking about the forward problem, again, it's a matter of creating the necessary contractive mapping that you have to use, that you have to have in order to ensure that you're gonna converge to the fixed point. So in the case that you can do that, I don't see any reason why the forward Fredholm neural network wouldn't converge. Now,
Right.
for the inverse, I think again the same, because the interesting thing for the inverse problem here is that you're taking advantage of the fact that you're taking some model, which you're saying this is my unknown kernel or something, but you're plugging it into a sequence of calculations whereby if it's not a contraction, for example, or if it doesn't satisfy the properties, it's going to get extremely penalized. So
Right.
theoretically, you should, get away from that and converge to a better solution. But of course, this is a training problem. So if you have a very difficult loss landscape or something like that, I imagine there would still be some important fail modes. But we haven't tested this exactly. But I think that because the Fredholm neural network itself, you can prove that it is a contraction. You're constructing it so that it's in a contraction. You'll probably be able to get some decent results, I would hope.
Understood. Yeah. Thanks. So basically, you're saying like, okay, I understood what you said. By construction, it shouldn't run into much issue. Yeah. So, but
Right,
the main
and this
advantage is,
is
sorry,
so-
go ahead. Yeah.
sorry, Vivek. I just want to say that this is something that we saw in our experiments as well, because for all
Uh-huh.
these trainable cases, so with the inverse problems, we ran the tests over 50 or 100 training instances, and we didn't seem to encounter any cases where, for example, it blew up. So it would be very easy to see if you just tried to learn the kernel in some kind of naive way, and then you plug that kernel into a Fredholm neural network, it would blow up because you would be
Correct.
applying these calculations, but possibly to an expansive mapping, which would blow up your solution.
Yeah. Thank you.
I have a question or a comment, Kyriakos, and
Yeah.
having listened to this twice now, I kind of I was wondering if you have um, drawn any analogies with neural operators, because you can build neural operators. FNO
Mhm.
looks pretty much like this, except they put a activation function in front of the in the recurrent in the.
Right.
So
Mhm.
in principle, you can build also operators, right?
Yeah.
You don't need the activation function. You just have to have a plurality of conditions. And
Mhm.
then have you thought about doing that? Because that, I mean, if you look at how FNO or then Laplace neural operator that we did, or the WNO, it have the same formula, basically follow Fredholm's integral
Right.
with nonlinearities.
Mm. So, Professor, this is something that, in terms of the operator, that we actually discussed based on some conversations we had at MSML with Professor Sietos and Professor Giannakopoulos. So it's something that I mean, we have considered, yes. So we do want to look into that for sure.
But there's intimate similarity, right? I mean, with the FNO, it's basically the same thing except the sigma.
Right. Yeah. Yeah. No, for sure. Yes. 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 I see that.
Okay.
Thank you, George. Do we have any other questions for the speaker?
I just have one small question about the extension of this method to other type of PDEs. Like, can we apply it to like hyperbolic, parabolic, or a mix of those? It should be somehow like related to Fredholm integration representation, right?
So yeah, yes, that's the idea, because you want to be able to kind of build this construction, this with the deterministic weights, etc. However, I there are ways that we can represent these in corresponding integral representation. So even for parabolic PDEs and everything, you can have some corresponding integral representations or even transformations that will allow you to look at it through this kind of discretization and integral lens, I believe. We've discussed a few of these approaches, but I think it should be possible for a good, fair family of such equations.
Do you have any one of them in mind? Like let's say a Navier-Stokes equation could be in there or not?
To be honest, we haven't looked at something specifically right now. This is kind of in the context of future work that we're interested in. But because I mean, this is what I'm saying this, based on some general discussions that we've had on how we could expand it.
Okay. Thank
Yeah.
you. Thank you very much.
Thank you.
There is a comment by Thanasis. I think
Yes.
that's the advisor,
Yes.
so he may want to answer the question.
Yes. No, I would just like to say, Professor Kraniadakis, that your comment was very insightful. In fact, what we do is very intimately connected to neural operators. And you may consider it as some sort of tailor made way of constructing such an operator for a specific type of problem, which is this Fredholm problem. So I think they're very much connected. And I think they're in the same spirit, more or less. Only that what we do here is more restricted to the particular type of problems that we look, in which case we can actually construct it through the fixed point scheme.
Yes, so that's a good point, Anas.
Thank you.
Thank you. Do we have any other questions for the speaker? I guess not. In that case, thank you once again, Kyriakos, for the nice presentation and the great talk. We really enjoyed it.
Thank you
And
very much for having me.
Thanks for staying late.
Thank you all.
thank you. And have a nice weekend. And thank you all for attending today's Scrum seminar.